class. This lab is solutions, electrolytes, and concentration. We are not on this chapter, so I'm going to try to cover it as much as we can. This is chapter 13, so if you need to refer to chapter 13, please do so, but I try to cover everything on here, so it may be a little bit longer of a lecture than normal. So solutes and solvents, we have a solution, which is, so when we look at solutions, we have a homogeneous mixture of two particles or more. So when it is a solution and it means homogeneous, it's one layer. You do not see more than one layer, as in you can see here with the blue solution. A solvent is made up of a substance that is present in greater amount out of a solution, generally. Now there are situations that's not true, but for this lab, we're not going to look more into that. So we're going to just say it's present in the greater amount. A solute is in smaller amount and is dissolved into the solvent, and the solvent and the solute make up a solution. Solutes and solvents can be solids, liquids, and gases. In this case, you can see sodium chloride. Let's say right here, this is sodium chloride. These are salt crystals, and they get dissolved into the solvent, and now we would have a sodium chloride solution. There's examples here of gases, liquids, and solids, and a solvent that they are dissolved in. Not going to go too much into this. So now we're going to discuss polar, nonpolar, and ionic. Let's just do a review of bonding. Ionic is a complete transfer of electrons. Polar covalent is an unbalanced sharing of electrons. So one of the atoms will pull the electrons closer to it, creating a partial positive and a partial negative on the compound. And then nonpolar is something about similar to, think of matching atoms. It's a tug of war. They are very equal in every way. So those electrons are never going to be pulled one way or another. And that means that there's no imbalance of the electrons sharing. Like dissolves like. We discovered, you had a lab prior to this that we kind of covered this. It's a like dissolve like. Polarities of a solute and a solvent must be similar in order to form a solution. So if you have a polar solvent and you have a substance and it's dissolved into it, it must also be polar in order for it to be dissolved into it. If you have something that's nonpolar and a substance goes into it, then it's also a nonpolar. So example again is salt. It's an easy one to think of. I found some nice little, animations here. You can see what happens when a salt particle, ionic particle, will go into something like water. The ions will be pulled apart and the water will saturate completely around these ions, and that will prevent the ions from coming together because there's still an attraction of the opposite of charges. But the water is stronger in holding them apart. They call this the hydration, a water hydration, for instance, where it completely surrounds it and prevents them from coming together. Now, if we look at something like sugar will dissolve in water because it has OH groups that are attracted to it, even though it has carbons, and carbons don't tend to be polar. Non-polar molecules, which have a lot of C's and H's on them, they don't dissolve in water because water is polar and oil is non-polar. So they'll try to stay far, far away from each other. So a non-polar requires a non-polar solvent in order for a solution to form. So this is just another example of how water will pull apart the lattice structure of an ionic compound, and keep those charges away from each other. You guys have seen this. If there's two layers, then that means they don't mix. If you see one layer, they mix. The words that we use are miscible and immiscible. That's what we were just looking at last week. I just didn't discuss the words because it wasn't really brought up. But if you have two layers, then they are immiscible in each other. And if there is one layer, then they are miscible. So ethanol and water, you see only one layer. But with oil and water, you see two. And you might see more no matter how many, depending on how many compounds that you add. So you see water has OHs, and this is a very polar. But oil is made up of a lot of hydrocarbons. And it does not want to have anything to do with a polar solvent. Here is a table here that could help you. So if you have a polar solvent and it is soluble, let's jump back. If you have a polar solvent and you have a substance that is going into that solvent, then it must be polar if it's soluble. But if you have a nonpolar solvent and you have a substance and it's insoluble, then this means that the nonpolar is the solvent. This must be polar because they're not mixing together, and vice versa for the nonpolar with the polar. So this is a good idea that if you have to look at something, you see it's soluble, then it's got to be polar if you're looking at polar. And if you're looking at nonpolar and it's insoluble, then one's got to be polar and the other's got to be nonpolar. Remember, like dissolves like. Now let's take a look at electrolytes and non-electrolytes. We have non-electrolytes, strong electrolytes, and weak electrolytes. A solution must have ions to conduct electricity. So it must dissociate, and understand what the word dissociate means. Pure water does not conduct electricity. So water is made up of H2O, which are molecules. They actually do not conduct electricity. Pure water will not. When you hear about people or you see in the movies they're electrocuted, it has to do with the ions. There's a lot of ions in water, calcium, the stuff that builds up in your showers. The ions carry electricity, and that's how you can get electrocuted. But pure water itself will not. When solutes are called electrolytes, that means they dissolve in water, they separate into ions, and they are able to conduct electricity. When solutes called non-electrolytes dissolve in water, they dissolve in water, but they do not separate into ions, and their solutions will not conduct electricity. So here's an example. We have light bulbs at the top, and you can see one is not lit, one is very bright, and one is very, very weak. This is an example of electrolytes, non-electrolytes, and weak electrolytes. So here we have methanol. Methanol is a non-electrolyte because there's no current going through to light this. So here's a solvent, and it should light this if it was an electrolyte. So even though it dissolves in water, it stays intact and it will not carry a charge. Then we have sodium chloride, very strong, goes right into ions. If it's an ion compound, it will dissociate and it will allow the charge to go through and light the light bulb. However, we also have weak ones here is acetic acid. You can see that it will light it very lightly. So this is a mixture of compounds and molecules and ions. So we can see a few ions, but it stays mostly as molecules. That's why this is a very, very weak lit bulb. It's a combination of both. So electrolytes, if it dissociates, it will dissociate into, you see the solid, and it will go right into aqueous solution because it'll be saturated with water around it. Formation of positive and negative ions, it allows a solution to conduct electricity. However, if we look at a weak electrolyte, so look at acetic acid, it is mostly undissociated, meaning it does not split apart its compound. The way sodium completely breaks apart, goes right into the ion charge. If you look here, acetic acid does not. Less than 1% of it actually dissociates. That's why the light bulb will be very, very light, very, very dim. And we have double arrows here. These double arrows mean that a few will disassociate, but most of it will stay as a molecule, and it just keep going back where some will disassociate, but some on this side will go right back into the molecule form. Which, here's an example. You can see it's mostly in molecular form and a few ions. So you can kind of see that there's an example of both in here. Non-electrolytes, we have an example of ethanol, and you can see sucrose here as well. They will dissolve in water. They are miscible in water, but they will not disassociate. So as you can see, ethanol here is a liquid. It's just straight liquid. And as it goes into water, it will dissolve into water where now it's in an aqueous solution. But it will not disassociate. It will be surrounded as an intact molecule around water, but will not carry a charge. Same for sucrose. And here's some definitions I put together so you can understand what's the definition of electrolyte, non-electrolyte, how to identify it. These are some pretty good things here, but rule is if it's an electrolyte, it's a strong electrolyte, it's a ionic compound. This is an experiment I did in another class, another college. There was a pickle, and the pickle is made of brine, which is a salt solution. So it's saturated with the salt solution. So it carries a charge because of the solution that it's in. I got to do that at another college. Sorry, now I'm trying to get off of it. Concentration of a solution. So the next thing we want to discuss is a concentration of a solution. Now, we wanted, if we were all to make punch in a room, all of our punches would taste differently because the concentrations would be different. So we need a value to understand how we can all make the same concentration of punch. One of the things is that if you understand concentration, it can be very, very dark where we have a lot of solute. Think of like dumping the whole punch powder into water. And then you might just take a teaspoon and then anything in between. So we would need to know values of this, numeric values of the concentration of what we're dealing with. So here, if you think about it, we can have a lot of solute, which would match something like this. Or we can have very little, or we can have in between, which would be something here. Okay, so we can also go by color. I mean, this is pretty visual. You can see this is very dilute. Nobody wants to drink this punch, and I hope nobody wants to drink this either. Somewhere maybe in between, maybe this one. But this is a good idea that if you were given samples of punch, you could understand this is very concentrated, this is very diluted. The picture is horrible, but it gives a good idea of concentration of a solution. And let's do a refresher on molar concentration. So remember, molar concentration is moles over liter. So let's say we have 0.9 grams of sodium chloride. We dissolve it in 100 mils. We want to know what the molar concentration is. The first thing you do is you convert from mass to moles. And then you take the volume, set it up over the volume, and then you can get your molarity of the solution. But now I'm going to introduce two different ones that you will have to do in the lab. We have percent by mass. When it says mass, that means grams over grams. So you'll take the mass of the solute and you're going to divide it by the mass of the solution. Solution, remember, is solute plus solvent. So if you're given that, you need to make sure that you understand what that one is. Because it can be tricky. Sometimes they may just give you the solute and the solvent values, but not tell you to remind you that it's a solution. And you have to remind yourself that it's a solution at the bottom on the denominator. It has to be both the mass, the solute, and the solution. and solvent. In some cases, they may just tell you what the mass of the solution is, and then the work's already done for you. But if it's not, and they give you a solute and a solvent values, you have to add them together. And here is mass by, this is a volume percent, mass by volume percent, exactly how it's stated, mass by volume. You have a mass of the solute on top, and you have the volume of solution. However, this is in mils, so you have to remember this is not liters, this is in milliliters. And these are all in your PDF as well. So here's an example of a percent by mass. We have, what is the percent by mass of a 285 gram solution that contains 85 grams of solute? You take the solute, set it up on top. The solution is on the bottom. Now remember, solution is both solute and solvent. It makes up of 85 grams plus 200 grams. The 200 grams is not listed here, but that's something that you should know. And now concentration by mass of volume. You have grams of solute over a mils of solution of a volume. So 3 grams of a powdered drug was added to a solvent. The final volume is 3.50 mils. That's the final volume. So that means that is the solution. What is the percent mass by volume of the solution? Simple. You set up the mass, divide it by the volume, and multiply it by 100, and that will give you the mass volume percent. And then here's a refresher to help you look at a table to remind yourself of what molarity is, percent by mass, and percent by volume. Now I'm going to explain a volumetric pipette. We definitely would have used one of these if we had been in lab. They are very accurate. They are more accurate than a graduated cylinder because they are specific to one volume only. So if you wanted to dispense 5 mils, you would have to grab a 5 mil volumetric pipette. They have this little bulbous body in the middle, and then there's a line, and these are all they're very accurate, usually to 4 sig figs. That's how accurate they are. So if you had a 10 mil, it would be 10.00, and you would leave it at that if you followed the procedures on how to use one. So what you do is you take a bulb and you'll put it on top, and you'll suction the volume that you want, and you'll let it go a little bit past until you get the meniscus to the bottom. The meniscus is at the bottom of the meniscus meets the line, and so it's a little concave. And then what you'll do is you'll remove the bulb and transfer that to the new bottle that you want to make a stock of. And you'll just let it go. Gravity will take this down. However, there's one more step you have to do. You have to touch the tip. You don't shake it. You just hold it very, very, keep it very stable. Don't shake it. Don't do anything to it. Then when all the solution's done, there's a certain amount of liquid that stay here. It's that's stuck here, and it's meant for that. It's designed that way. You touch the side of the inside of the container with the pipette, and there's usually one drop that's kind of forming here. That you touch it, that will take that one drop, and you never do anything again. You take it out, put it on the bench, and you'll see there's still liquid here. But it's meant to be that way. It's accurate. That's how it's supposed to be. One touch on the side, and you're done. And that will give, if you've met everything the way it's supposed to be, the 5 mils exactly that's been delivered to another container. They're really hard to use in the beginning too. Students really struggle with these because they take it. It's very easy to suck up the liquid. It's very hard to get it to the line and make sure that it matches it. Oh, look at, I forgot a space here. So choose the glassware based on accuracy. This is in part of the video. This tells you what is very accurate. Here's a hint. There might be a quiz question if some of you get that. So I took a copy of it here. All right, so now let's get down to the parts of the lab. First part is polarity. You're provided with 4 substances, and you will need to determine if they're soluble and insoluble. So here's the thing. They tell you whether it's soluble or not soluble. And then you'll have to figure out if they're polar or not. So that's pretty easy because we've already gone over it. They already tell you. You don't even have to look up if they're soluble or not. Part B, you have electrolytes, and you will think about intensity of a light bulb. They're not showing you pictures of light bulb. You actually have to think about what they'll tell you if the light bulb is dim, bright, and so forth. And then you'll have to figure out if it's electrolyte, what type of electrolyte, and then what consists of it. Is it molecules, ions, or both? So I'm giving you one of them. This is a weak electrolyte. It tells you it's dim, so because it's dim, that means it's a weak electrolyte. And it's made up of molecules, ions, and both. And you'll have to figure out the rest of them. All right, let's get to part C. Part C is a fun lab. I like this lab. It's not a bad lab. It's a pretty easy lab to do. You will have a salt solution, and they're going to give you enough information that you're going to be able to determine several calculations from this. Molarity, mass percent, mass by volume percent. You're going to have to, that's what this whole thing is building up to. So this is a solution that's going to get evaporated in an evaporating dish if we were in class. And it would go like this. You would just see it would get where it dissolves, and then you let it dry completely and it forms salt again. And then you want to know how much salt was in that solution. So these were my numbers that I was given, and your PDF gives you the molar mass, so you don't have to look at that. We have an empty evaporating dish, which this is an evaporating dish. It's meant to be heated. And I was given 10 mils of a solution, and then I have my massive dish and salt solution. So that would be something similar to this. And then before the experiment, and then after the experiment, that is this here. And so just pretend these are evaporating dishes, because you cannot heat these. These are not meant for heat. But that's a visual for you to get an idea. All right, and if you get confused, your lab, your PDF is nice enough to break down all the equations that you need to solve for each thing in LabFlow. I have mine numbered differently because I don't like the way they numbered it in LabFlow, because they ask questions that you cannot answer without answering other questions, and they have those questions after the questions that you need the information for. So it doesn't make sense to me. They didn't set it up correctly. The flow of it is stopped because you have to jump to the end to answer some of those questions and then go back to other questions. But it doesn't matter. This really does help you understand, if you read it, what you need to do. This is a very simple lab. You've done way harder labs than this. So I broke it down. My numbers do not match the how-to. So you'll have to read what my numbers, I tried to match it up here. But these are all my calculations, so you can see how I got my numbers. And some of this stuff has been given to you. You just have to convert it. For instance, volume of solution, you have to convert it to liters. And yeah, so they'll ask for mass percent, but you need some of this other information, like you need moles. You need other things that they expect you to answer after, which you can't do some of these without that. And if you get confused, this one says mass of dry and NaCl. This is mass of dry. This is volume in mils. So make sure you understand and double check before you answer it, so you get exactly what an answer, how it's asking for on here. And that's it. So go over the PDF and make sure that how you're answering it is exactly what they're asking for. It's really, you can, because it's all on one page and it's kind of jumbled, you can accidentally enter the wrong calculation, not meaning to, and that could be a problem. Okay, that's it.